Hello everyone, my name is Leo. I'm thrilled to have this opportunity to introduce myself. I live in Shatin. I have three family members, my wife, my son, and myself. I graduated as a first degree in applied chemistry in the Hong Kong Baptist University in 1996. I got my PhD degree in chemistry in Hong Kong Chinese University in 2001. I have a passion for chemistry, and all my past working experiences are surrounding chemistry. It includes my tutorial experiences and my private lessons. I'm a chemist. I've over 20 years working experiences in a companies of different nature. I've started my first job in a wastewater treatment plant in 2000. Then I've entered into another business sector, the consumer product testing industry. I've been working in some international testing laboratories at that time. I'm involved in the chemical testing developments, the chemical product testings, and the technical services. In addition to chemical management, I've also explored and experienced in operation management, business development, and general management. In my last job, I've been working in a fashion brand for sustainable chemical management in the supply chain. It can leverage and gauge the chemical safety in apparel and footwear products. In my leisure time, I love hiking, cycling, and jogging, as I can enjoy the lovely scenes during the exercise. I even challenge myself with some difficult trails. I may plan to explore hiking in other countries, such as Indonesia, because I'm attracted by the scenes and the routes there. I also like some sports games, such as badminton, tennis, and pickleball. I enjoy playing indoor activities with my family members. It includes board games, building Lego models, table tennis, and snooker. It can further bond the relationship within my family. I consider myself curious and detail oriented, with a methodical approach to learning and connecting them to the real world applications. I'm sociable, as I like to exchange the ideas and experiences with my friend for continuous learning and development. Looking ahead, I aim to continue to use my expertise in chemistry in my upcoming job. I'm applying for the part-time positions at the Cana Education Center, as I wish to contribute to the field of education using my expertise in chemistry. Recently, I've observed the situations that many children are very dependent on the tutorial lessons to improve their academic results or even meet their very high targets. This situation triggers me to have this move. I'm thinking whether the job of education is suitable for me. That's why I'm applying for the part-time positions. That's the end of my self-introductions. For next part, I will do demo lesson. Hey class, today the topic of our lessons is the reasons for the transitions element complexes are colored and the factors affect the color. Before jumping into the detail of the lessons, I have a couple of questions to you. Where is the transitions element in the periodic table? Yes, they are the D block elements located in the middle of the periodic table, correct? But why they called the D block elements? Benny, can you try? Yes, Yes, great. Because they have the partially filled d orbitals. How do d electrons relate to the color of the transitions element complex? Anyone can try this? No? Okay, let's discuss in the following slides. Why are the transitions element complexes colored? Transitions metal complexes are colored. It is due to the electronic transitions within the d orbitals of the metal ion. It can be further illustrated in the following process. When the ligands surround the transitions metal ion, they interact with this d orbital, causing them to split into different energy levels. It is called the crystal field splitting. The extent of this splitting depends on the geometry of the complex, the nature of the ligands, the oxidation states of the metal, and the type of the metal ion. Electrons in the lower energy levels absorb the specific wavelengths of visible light and jumps to the higher energy levels. It is called the DD transitions. The absorbed light corresponds to the energy difference between the split d orbitals. The color we see is the complementary color of the absorbed light. For example, if orange light is absorbed, the complex appears blue. In addition to the DD transitions, in some cases, the color can be arised from the charge transfer transitions. There are two types, the metal to ligands or the ligands to metal, which are typically more intense than the DD transitions. There are four factors that affect the color: the oxidation state of the metal, the nature of the metal ion, the geometry of the complex, and the last one is the type of ligand. The oxidation state of the metals affects the color of its complexes because it influences the d orbital splitting and the energy gap between the d orbitals. There are several scenarios. The effective nuclear charge. A higher oxidation state increases the effective nuclear charge of the metal ion. It pulls the ligands more closer. It strengthens the ligand field and causes greater splitting of the d orbitals. It alters the wavelengths of light absorbed. Electron configurations. The oxidation state determines the number of d electrons available for the transitions. For examples, a metal in a high oxidation state may have fewer d electrons, which can change the type and the intensity of the electronic transitions. For examples, the chromium-3 has 3 d electrons, and chromium-2 has 4 d electrons. Charge transfer transitions. High oxidation states can enhance the charge transfer transitions, which often produce intense colors. Ligand interactions. The oxidation state affects how the ligands interact with the metal ion, influencing the overall geometries and electronic environment of the metal complex. The second factor is the nature of the metal ion. The nature of the metal in the complex affects its color. It is due to differences in its electronic structures and the interaction with ligands. The number of d electrons. Each electron metal has a unique number of d electrons, which determines the possible electronic transitions. For examples, the iron 2 and the copper 2 ions absorbed different wavelengths of light, leading to distinct color. The nuclear charge. Metals with higher nuclear charges create stronger ligand fields. It increases the splitting of the d orbitals. This alters the energy gap and the wavelengths of the light absorbed. For examples, The copper 2 is heavier than the iron 2. It causes larger energy gap of the split d orbitals and shorter wavelength of light is absorbed. The spin state. Some metals can form high spin or low spin complexes. It depends on the strength of the ligand field. This changes the energy of the DD transitions and consequently the color. Charge transfer transitions. Certain metals are more likely to exhibit charge transfer transitions. For example, the iron 2, which can dominate the observed color. The third factor is the geometry of the complex. The arrangements of the ligands surround the metal ions affects the splitting pattern of d orbitals. It alters the wavelengths of the light absorbed. In the tetrahedral complexes, the d orbital split into two energy levels, with the lower d orbitals located at the lower energy level and three d orbitals at the high energy levels. In the octahedral complexes, the d orbitals split differently, with two orbitals at the high energy levels and three orbitals at the lower energy level. This energy gap between the orbitals in the octahedral complex is larger than that in the tetrahedral complex. It alters the wavelength of absorbed light and it results in different colors. The last one, the types of ligand. The type of ligands significantly affects the color of the coordination complex due to its influence on the d orbital splitting and the electronic transitions. It is also related to the spectrochemical series. It arranges the ligands in the order of their abilities to split the d orbitals in the octahedral complex ion. The ligand field strength. Strong field ligands, such as the cyanide and ammonia, causes larger splitting of the d orbitals. It leads to the absorption of high energy light. The weak field ligands, such as the water and the chloride ion, it results in a smaller splitting. It absorbs lower energy light and longer wavelengths of light. For examples, the hexyl aqua chromium 3 is dark blue color, and the hexyl ammonia chromium 3 is violet. Charge transfer transitions. Ligands like carbon monoxide can accept electrons from the metal. It enhances the metal to ligand charge transfer transitions, which often produce intense color. Ligands like halides donate electrons to the metal. It facilitates the ligands to metal charge transfer transitions, which also contributes to the colorations. In conclusion, the transitions metal complexes are colored due to DD transitions and the charge transfer effects. The color depends on factors such as the oxidation state of the metal, the nature of the metal ion, geometry of the complex, and the ligand type. Hey class, this lessons we have discussed the color which affects the transitions element complexes and also the factors which affect the colors. I have one question. Are all transitions element complexes colored? Anyone can try? Any idea? Benny? Sayden? No. Okay. The answer is no. Not all the transitions element complexes exhibit colors. Here is the suggested answer. The scandium and zinc iron are typically colorless in their aqueous solutions because they lack the partially filled d electrons. There are two scenarios. In the case of scandium-3, it has the empty d orbitals. That means there's no d electrons. There are no possible no dd transitions to absorb the visible light. For zinc-2 ion, it is a completely filled d electrons in the d orbitals. So there are no available energy gaps for the electronic transitions that would result in color. Any questions? No? Okay, we jump to questions 2. What is crystal field theory? Can you explain the theory using one transition metal complex? Anyone can try? We've discussed this in previous slides, the crystal field theory. No? Okay. The crystal field theory explains the interactions between the transitions metal ion and its surrounding ligands in a coordination complex. It focuses on the electrostatic forces between the positively charged metal ion and the negative charges of the ligands. Here's the examples. It has an aqua nickel 2 plus. In a free nickel element, all the 5d orbitals have the same energy level. It is called the degeneracy. When the 6 water ligands approach the nickel ion, the electric field disrupts this degeneracy and causes the d orbitals to split into 2 energy levels. It is called the crystal field splitting. We've discussed this before, right? Electrons can transition between these split d orbitals by absorbing specific wavelengths of light, which gives rise to the color of the complex. In this case, the nickel 2 ions absorb the wavelengths of red light and transmits the complementary wavelengths of green light. Any questions? No? If you have further questions, don't hesitate to approach me. Thank you, class. We can dismiss.